Alaskar from Professor Stephen Ringe's group, Digis, South Korea. In this talk, I will give a short presentation on mean field microkinetic modeling. One of the famous package of microkinetic modeling is CatMAP, or we can call it as Catalysis Microanalysis Package for electrocatalyst design. So what is microkinetic modeling? Microkinetic modeling is a technique. It is used to extend both experimental and theoretical observation to predict results of chemical reaction under various conditions. There are two types of microkinetic modeling. One is mean field microkinetic modeling, and second one is kinetic Monte Carlo modeling. But in this talk, I will focus on mean field microkinetic modeling, which is more simpler than kinetic Monte Carlo modeling. And the package, which I already mentioned about, is CatMAP, or Catalysis Microanalysis Package. So in this package, we generally analyze and we screen a catalyst, which may be composed of any material. By the help of Catalysis Microanalysis Package, we can design different catalysts, and we will be able to identify reaction intermediates. How many intermediates during the reaction mechanisms, and what are those species? And we will be able to identify rate determining elementary reactions, because one reaction has many smaller reaction mechanisms or smaller steps. So we will be able to find all those elementary reactions. And at the end, we can find kinetic parameters from experimental data and theoretical correlations and quantum and chemical calculations. Before starting the hands-on tutorial on Catalysis Microanalysis Package, the audience should be able to understand what are these parameters or what are these terminologies, because these terminologies are used commonly in the Catalysis Microanalysis Package tutorial. So you must be able to understand what are these terminologies actually. So I will just shortly and briefly explain these terminologies. First of all, degree of rate control means, as I have mentioned earlier, that there are a lot of elementary reactions mechanisms in one major reactions. So which reaction steps or which elementary steps control the rate of reaction? That is degree of rate control. So degree of rate control quantifies how much the energy of each species in a reaction mechanism. And the second one is active site. Active site is definitely, there are a lot of sites on a catalyst surface, and some of the sites are more active and some are passive regarding making different products. So active site is a region of catalyst where a substrate or different species binds and undergo a chemical reaction. And the descriptor, which is most important in this Catalysis Microanalysis Package, is a physical quantity actually. Maybe temperature, concentration, pressure, anything which we study in reaction kinetics. So any parameters, maybe one or two parameters, which are used to define all other parameters. All other parameters are depend on these parameters. That is called descriptors, because rate of reaction cannot be explained based on many parameters. If we try to explain by many parameters, then the system becomes more complex. So it's better to identify one or two parameters. So based on these two parameters, we can easily explain rate of reactions. So any physical quantity or parameters may be descriptors in your system. So you have to identify what is your parameter. And turnover frequency, generally used in CO2 reduction reactions and other catalysis, electrocatalysis, water electrolysis. This research area covers this turnover frequency, current density, or potentials. So these are electrochemistry terminologies. So turnover frequency is calculated by a ratio of number of moles of target product produced per unit time of maximum number of mole of active catalyst. So how many mole of products are producing based on the given number of mole of catalyst, that is turnover frequency. So if turnover frequency is higher, then it's better for our system. So it is used to generally to define activity of the catalyst, and current density is ratio between current per unit area. So this per unit area is equal to surface area of working electrode. So this parameter current density is also used to identify the activity of catalyst. Higher the current density, higher, more ideal your system will be. Our potential is the difference between the actual and required actual potential and the required potential. So each system has a chemical potential, equilibrium potential, but you need some different potential, maybe higher or lower than the equilibrium potential. So that is our potential. We can see in this diagram, our schematic diagram of CatMAP. All these dark gray boxes corresponds to classes in the CatMAP. So there are 5 classes: parser, scalar, thermodynamics, solver, and mapper. While the white boxes represent different types of intermediates data along with some representative examples. So representative examples are raw data, descriptors, reaction parameters, outputs. And what are your descriptors? For example, in this case, they use adsorption energy and D band center as descriptors, and they go turnover frequency, selectivity, degree of rate control. So you should focus on these outputs. What actually parameters you will get after using Catalysis Microanalysis Package. And just pause the video and read these definitions, then you will get some idea. Now I will start the hands-on tutorial of Catalysis Microanalysis Package. First of all, generating an input file. You have to generate an input file and then creating Micro Kinetic Model file. At the end, refining Micro Kinetic Modeling. So these 3 phases or steps are required for Catalysis Microanalysis Package process. The first step for any kinetics model is properly generate an input file. First, you have to generate an input file by parser any class. Maybe there are 5 classes. They works and their function are different. So classes of CatMAP. And the job of parser is to convert some standard data into a Python data structure compatible with the kinetic model. Because we use Python programming language in this Catalysis Microanalysis Package, therefore parser actually convert the standard input into Python data structure, which Python can read. And then you get like this, but I will explain these things later. Before going to these things, I will show you some basic tutorials, which we see. But the system was not working. So anyway, you can find easily the Catalysis Microanalysis Package documentation tutorial, and then generate different steps, follow different steps, and then you will generate at the end input file. So the input file structure will be like this. The file structure like this: surface name, sites name, species names, formation energies, vibrational frequencies, and reference. So how we can generate this input file, I'm not going to explain all those process because it's a very long process. Just you can follow the tutorials which is given on Catalysis Microanalysis Package documentation tutorial. So anyway, after generating your input file, file structure should be like this. So in my case, I'm using copper 211. So site name is 211 and different species are adsorbed. And for their formation energy is calculated by either DFT or any literature given, already reported in previous literatures, and vibrational frequencies and reference. So the first line provides title of all columns, See, this is the first lines, titles of all columns. So this one is title of this one, site name is this one, species this one, formation energy is like this. All column order does not matter, but header's name do matters. You can change their orders, like you can write species name second and site name at the third position. So it doesn't matter. But the header name should be matter, because if you are writing site name here, third position, then you should write all site names below that site name or the input first line headers. Any number of other input column may be added. You can add some other thing like bulk structure, and then you can add HCP, FCC, or BCC metals. So you can add any columns inside these columns. Now I will explain all these field values which were generated in our input file. First of all was surface name. So this is the name of the surface to which species are absorbed. For example, in our case, we are using copper catalyst for CO2 reduction reaction. So surface name is copper 211. And site names, the names are used to distinguish different site types, like 211, 110, 111. So there are a lot of types of sorts, but we can also call them as orientational facets. And species names, the species are the intermediate which are going to adsorb on the surface of the catalyst. And the formation energies, which is one of the most important parameters in generating input file. So this is one of the backbone of input file because it defines energetics of the system. But there are some reference values we have to consider. Like for hydrogen, we should write like this. For carbon, we should take methane as a reference and then subtract, because methane has 4 hydrogen. So 4 hydrogen. And for oxygen, we always take water as a reference. For hydrogen, we take hydrogen molecule as a reference. For carbon, as we can take methane as a reference. And for oxygen, we take water as a reference. And then subtract like this. How many hydrogen atoms it has, how many hydrogen atoms it has, like this. For example, in CO2, the formation energy should like CO2 minus C minus 2O, because carbon is, there is one carbon and 2 oxygen. If the CO2 is adsorbed on copper 211 facets, then energy should be like, first of all, energy of carbon dioxide on adsorbed on the catalyst surface, and then catalyst surface energy separately, and then carbon energy, and then because there are 2 oxygens, so oxygen energy. And then frequencies, the list of vibrational frequency actually of the species name on the surface name at the site. Definitely the species will adsorb on some specific sites of the catalyst surface. And then reference is not much important. Just for your understanding, you can add this column. Now, how actually the species are adsorbed on the surface? We can see that, for example, this is a nickel surface, but in our case, we are using copper surface. But you can get some better idea about it. And there are some species adsorb on the surface, and then they start to make bond like this. And sometimes different species come, and then they give some steric or inductive effects on the already adsorbed species, and then they start to make new bonds, and then we can get different type of products, C2 or C1 products, anything. So we have already generated input file, and now we are going to start second steps, which is a creating microkinetic modeling. So creating microkinetic modeling consists of set up the file, a model, and analyzing the output. So first, the second step, microkinetic model creating, is one of the most toughest step of the CatMAP. So first you have to set up the model, and set up model has 2 more steps. One is setup file, and another is submission script. And the setup file itself, we have to define all these parameter reaction expressions, because there are many elementary reaction steps. So you have to define all those reaction steps inside your system. Sometimes you can neglect some important steps are in adsorption, like some intermediates, but sometimes you can add some more intermediates based on your system. And descriptor names, which I already explained at the starting, how many parameters you are using as a descriptors. So all other parameters will depend upon the descriptors. And then there must be a descriptor range. For example, I'm using temperature and pressure as a descriptor, then there should be a range. Like, for example, in my case, I'm using -5 to 2 volt as a descriptor range, and for temperature, only 298 Kelvin is fixed temperature, so there is no range. Resolution means number of values repeat between these descriptor values. So as long as you will increase the resolution, you will get good data or beautiful data. And the temperature and data file and input file, these things are defined. But how to define these things, you can follow the tutorials which already given on CatMAP tutorial website. And for submission script, energy text, there is folder energy text, which I already shown at the starting. Surface names, site names, vibrational frequencies, these things. That is called energy text or input file. It should be in text file. And then CO2 microkinetic modeling file, which you will get this file after doing these steps. These all steps. If you proceed all these steps, then you will get a new data that is called MKM file and microkinetic model. That our second name is setup file. And then one small job script you have to put in another Python file and run this file. This is called submission script. Then you will automatically get, there are 3 folders, 3 files in your folders. Then if after running this job, you will get 5 folders like this: energy text, MKM, job script, submission script, and then these 2 files, log file and data file, are generated as an additional 2 files. So what are these 2 things actually? Log files are very similar to microkinetic file, MKM file, but they have some additional new variables. But data file is actually the extension of this log file. So what are benefit of this log file? You can load it as a setup file to a reaction model, and we will output as interactive Python mode. That's not that much important, but you can use your own Python as well to read this log file. And at the end, a refining of microkinetic modeling. These are outputs you can get after running this microkinetic Catalysis Microanalysis Package. You can get free energy of the system. You can get rate control and selectivity control, production rate, which is rate of reaction actually, and coverage of intermediates. Coverage means the different species are adsorbed on catalyst surface, and sometimes some specific species cover all surface, and sometimes they cover partially surface. So its value must be from 0 to 1, and then you can define. Reaction rate means net reactions, forward rate of reaction minus backward rate of reaction. Then turnover frequency, consumption rate, and interaction energy. These all parameters you can get as an output. This is I got for methane or C1 product, and this is for ethanol or C2 products. These 2 are simulated curves, polarization curves. Polarization curves means the curve between current density and voltage. It is called polarization curve, and these 2 are experimental, and they are in good agreement. This is hydrogen evolution reaction, simulated one, and this is experimental HER or hydrogen evolution reaction. This HER is obtained by fitting Hierarchy activation of barrier. So how to run this MKM file, I will show you. For example, I will make a new folder, which must be make directory tutorial. Now I will copy text file which we already generated at the starting of the process, and then MKM file. I will show you how to read these things, and then job file, MKM file, to tutorial, cd tutorial list. Now we can see there are 3 files, text files. How to read? Just click on it and then read how it looks like this. Maybe it's not visible on screen, but I have already shown. And how this MKM file. This script must be put in your MKM file and then run this job. Now I'm going to run mkm.py. Now running. It sometimes takes 5 to 10 seconds, and sometimes it takes more time, but it's up to your system and PC. Maybe it takes more than 1 minute. Anyway, then you can read this log file. You will get it. As I have already mentioned, that we can get log file and pk1 file. Both are almost similar to MKM file, but they have slightly different. So it's working. So till date, I'm trying to share other screens. Now it's better. Our job is running there, and till date, this job is running here. So till date, we can explain these things. Or I will show you some more. Just search CatMAP documentation. You can get then this one. Here is tutorial and input file. How to generate input file. They said everything, mention everything here. And using all these process, you will get new data, which is text file. This is text file, which I have already shown that in our system. I will try to show this one. Maybe our system is PH7. Yeah, PH7. CD list. CD7. CD list. So we can see list. Now we can see how the text file looks like. This is text file, our text file, and Catalyst surface name, sites name, species name, formation energy, all things are mentioned here. And we are just interested in one copper 211 orientation facet. And how to open this MKM file, which you have most difficult step is to generate this file. So this is called MKM file, a Micro Kinetic Modeling file. It mentions all things like hydrogen evaporation reaction mechanisms and all other CO2 reduction reaction towards C1 and C2 products. And TEFL, Heroisky, Wolmer steps, surface name, copper, just copper. But actually some people are using Catalysis Microanalysis Package for comparing many catalysts or many materials. And descriptor is voltage, temperature, and descriptor range here, pH, everything is mentioned here. Resolution, which I have already mentioned, 200. So these are actually MKM file. But our file is still running, but I'm not sure how much time it will take. But anyway, after generating, we will get data like this. Log file, it seemed like this. You will get log file, which has file structure like this, almost similar as MKM file, but some additional data, coverage, turnover frequency, these are mentioned here because MKM file is input file, but log file is our output file, so it must contain some output variables like turnover frequency and other things. But for PK1 file, I'm going to show you. Yeah, it's not readable here, but I will try to read by text editor, not readable here. Anyway, so then after that, so these are HVR and other things. And this is rate control. The rate control has already, they have given the script for rate control for HER competing with C1 and C2 products and rate control of pure HER. So for Wolmer step, sometimes Wolmer step is rate controlling step, and sometimes Heroisky step, sometimes TEFL step. It's up to your system. And this is production rate. The script alpha production rate also given in the tutorial already. So you can just copy paste and put in your script and then run your script. You will get file. In my case, this is for ethanol, this is for methane, CO, carbon dioxide, carbon monoxide. Someone has good production rate, someone has not much better production rate. And this is for HER process, water, hydrogen, OH, electron. These are HER process. Their production rates are given here. And this coverage, you can see all species. They are all not products. They are species which are adsorb on the catalyst surface. So they are intermediates. So intermediates coverage, it not exceed than 1, because 1 is maximum. 100% coverage we represent as 1. This is carbon monoxide, which has slightly more coverage because our actual target is carbon monoxide. First, carbon dioxide is converted into carbon monoxide, and then you can proceed to a reaction towards C1 and C2 products. This is for HER. Reaction is negligible. They have coverage, these all species have coverage, but they are negligible. But this one, I maximize these things, so you can see some slight coverage value here. And some doing micro kinetic modeling or plotting on their control plot and stake plot, we can get data like this. So this is control plotting of turnover frequency as a function of carbon dioxide partial pressure and pH. So we have to generate some text file there, or you can just use for on control plotting, and then using your codings, yes, you will get, and you can find the trend of different species. So this is turnover frequency. So activity, it shows activity. So they are active. In this case, they are active in lower partial pressure region, but independent of pH. Almost all species are independent of pH in this case. It's fixed voltage -2, but you can vary this voltage -1, 0, anything, then the trend will be different. And this is a rate curve. Script is also given in their tutorial. You don't need to be worried about that. Just run your script and you can get different rate for different species. Thank you very much for your attention, and I will be waiting for your questions.